Okay, so the purpose of this recording is to give some homework hints if you're fixing your homework on number 51 and 55 on page 111 and 112. So first I'm going to talk about 51, and in this problem we have a ball projected horizontally from the edge of a table 1 meter high, strikes the floor at a point 1.2 meters from the base of the table. So this is actually very similar to the lab that we did. So we have some sort of table, might even draw legs on it, and this is sitting on a ground, and the ball is projected horizontally, so in other words it's going just straight horizontally on this 1 meter high table. So in other words, and the book gives some sig figs, but I'm being a little bit lazy, so I really could write this as 1.00 meters. And it strikes the floor at a point 1.20 meters from the base of the table. So that means that it falls off with that curved parabolic trajectory. And just as we learned in the lab, when we measure that it lands that far from the base of the table, that's not from the legs. You kind of have to take this imaginary vertical line and measure from there. So that is 1.20 meters. And they ask, what is the initial speed of the ball? Well, we know delta x for the ball. We know delta y for the ball. We also know acceleration in the x direction, acceleration in the y direction. We know that v initial for the x is the same as v final for the x. And because it's going horizontally, that's going to be whatever our v initial is. So it asks for the v initial of the ball. We're going to rename this Vx, but that Vx is actually what we're looking for. And we also know that V initial in the y direction, because it's only going horizontally, it's not going up and down, this is 0 meters per second. And then, let's see, do we know anything about time? No, we know nothing about time. They told us delta x, they told us delta y. We don't know anything about V final in the y direction, and so we must proceed from here. So this is what we're looking for. And remember our equation, we're going to have to find delta t before we find Vx. So go over to your y direction. You have 1, 2, 3 bits of information. Find delta t, and then come back, plug it in to find initial velocity. Now part B asks, how high is the ball above the floor when its velocity vector makes a 45-degree angle with the horizontal? So this one is a little bit more challenging, and so think about what that means. If it's making a 45-degree with the horizontal, so we're trying to find whatever spot it is for which the velocity vector makes a 45-degree angle with respect to the horizontal. Well, if this is a right triangle, I'm going to draw it pretty large so we can get that notion of what's going on. If this is 45, you guys remember from geometry that if I have a 45 degree, a 90 degree, this one also has to be 45 degrees. So in a 45-45 right triangle, think to yourself, what do I know about the two sides? Well, in a 45-45 triangle, since they're both opposite 45-degree angles, which are the same, those sides are the same. Well, we want this to be the velocity vector. So what that means is that at that instant in time, velocity in the x direction is equal to velocity in the y direction. So we can treat this kind of like v final. So I'm going to actually, instead of just Vx, I'm going to talk about V final in the x direction and V final in the y. In other words, what I'm saying is ignore the whole landing bit. Ignore how far it took you to get there. Ignore how high the table is. We want to figure out that stuff. So at this point, we would know V initial because we just solved it, whatever you get from part A, you know V initial. So I'm going to write here that this is part A's answer. And so in part A, we would have learned, the book tells me this may be off for sig figs, but 2.66 meters per second. So that means that V initial in the x is equal to V final in the x, which equals 2.66 meters per second. Well, what that means is if V final in the x is 2.66 meters per second, so is V final for y. The only difference is that because this projectile is going down, that means that V final for the y is negative 2.66 meters per second. Well, now you have VFX and VFY. If this is 2.66 and this is negative 2.66, can you take those two components and find me this? It's Pythagorean theorem. So use your Pythagorean theorem and figure out that velocity. Now, to be totally accurate, it says, oh, I'm sorry. The question, this happens to many people, the question actually asks for how high is the ball above the floor. So we're looking for, no longer do we know delta y, we're looking for delta y. Well, you know 3 bits of information, VFY, VIY, acceleration. Use an equation to find how high it is. So actually, you didn't need to do that component thing. From that, you end up getting, and this is the book answer, so sig figs, you end up getting that it's 0.64 meters. So I hope that helps you walk through that one. So now let's talk about 55 quickly. This one is not too bad if you really understand one-dimensional motion. It's just the reading of the problem and translating it. So a car parked on a cliff overlooking the ocean on an incline. So we have a cliff that's on an incline. So it doesn't just drop off, but we have some sort of sharp cliff. And then all of a sudden, that drops off. So right here, we have a car. And what's happening is that the negligent driver leaves the car in neutral and the emergency brakes are defective. So the car rolls from rest down the incline. It's going to move this way until finally it comes off the cliff, and then it's going to follow that trajectory that we know about. So what you want to think about is break this up into 2 parts of the problem. Think of this incline as part 1. So from that we know V initial. We also know that this is at an incline of 24 degrees, which we actually don't need for this part. This is what we'll need for the next part. But we also know that it travels 50 meters. So this distance here is going to be 50 meters. We also know that it accelerates at 4.0 meters per second squared. Well, if the car starts from rest, the initial velocity is 0. You know V initial, you know acceleration. This is basically displacement. So even though it's slanted, what we're going to think about is, instead of just thinking of x and y like this, we're just going to think of one-dimensional motion. The car is moving in one direction. So if you know displacement, you know acceleration, you know initial velocity. Can you find the final velocity for which it comes off the cliff? Can you take those 3 and find an equation that uses VF, VI, A, and delta x? That equation is VF squared equals VI squared plus 2A displacement. So find basically this velocity. Now once you do that, you have to move on to the second part and pretend that that rolling never happened. So once you get to this part, you kind of have a new, this is part 2 of the problem, for which instead of this being the final velocity for part 1, I'm going to label this as initial velocity for part 2. Well, that initial velocity is at an angle of 24 degrees below the horizontal. So if this is the horizontal, I can think of this as, oh, I'm going to take a separate triangle. Here's that V initial, whatever you calculate. Here's the angle, 24 degrees. Can you find me V initial in the y direction, V initial in the x direction? Once you do that, you're back to your normal problem solving stuff. You know Vix, you will know that that equals Vfx. You know VIY, you know, did they tell us how high the cliff was? The cliff is 30 meters above the ocean, so we know delta y, but make sure that's negative. We also know that it travels, nope, that was for the first part. We want to find the car's position relative to the base when the car lands in the ocean, so we're looking for delta x. We know acceleration in the x direction, we know acceleration in the y direction. If I'm trying to find delta x, guess what I got to find first? Find delta t. So go over to the y direction. You have 1, 2, 3 bits of information. Find delta t. Once you get delta t, go back and find delta x. So the hardest part of this problem is realizing this first part. I really think that's the hardest part of the problem. After that, it's like every problem that we've done.